Okay, so guys, here's what we're up to today. The date is the 23rd, which means amazingly we only have one more week in September. It is going fast. I do like October. So guys, you know that I'll always give you the topic for your notes, and as you can see in front of you, the topic for today is subatomic particles and atomic structure. But what I wanted to do for you, and this is what I did down beneath that, is laid out for you what we're going to learn today. And guys, at the end of the day today, you are actually going to be able to answer these three questions. Where do atoms come from? What do they look like? Kind of. At least, how big are they? And then finally, what are they made of? Hi, Ron. So guys, we're going to pick off these questions one at a time. When we've answered all three of these questions, we're going to be done for the day. You'll get your homework done. It's a glorious thing. So tell me when you're ready. No, I wouldn't. I don't think you need to. If you just have the title of your notes, you're good. You guys all settled and ready to go? Okay, so guys, this comes with a disclaimer. And I got to be careful what I say here, but I need to say something. So when we talk about where atoms come from, we are going to talk about Big Bang Cosmology. Okay? You probably have heard of the idea of the Big Bang. You understand that there was this thing that blew up about 14 billion years ago, and that's where the universe came from. Now guys, the problem is that this is not just a scientific idea. This is also a very just tension-packed political issue, because there's this tension between creation and evolution, and was it on purpose? Did God do this? Was it random chance? Is there any room in the middle to be a scientist with faith? And guys, I don't get to tell you what I believe, unless you ask, but we're not going to go there right now. But guys, what I can tell you is this. We are going to treat the Big Bang as if it happened, because all good scientific evidence points to the idea that it did. I would suggest to you, though, that you can believe in the Big Bang and not abandon any faith in God that you have. I do not believe that those two things are contradictory. As a matter of fact, I think they go hand in hand very, very well. So if you'd like to talk more about that, we can do it later. We just can't have that conversation now, because that's preaching and I'll go to prison. Okay? So with that said, guys, again, we are going to talk about the Big Bang just like it happened, because we really believe that it did, and we'll sort out the rest of that individually if you'd like. Okay, so where do atoms come from? How big are they? What are they made of? That's the day. You ready to go? All right, so guys, first of all, where do atoms come from? And in order to answer that question, we are actually, well, let me say it differently. You've got to be able to answer these 5 questions, and you want to write these down. Leave 2 spaces between each question. So guys, here's how this is going to go. How does this all tie together? And then I'll show you the questions. So guys, the idea is this. You learned about this Monday when I was sick and dying, and you got the idea about homo heterogeneous. We talked about substances, physical, chemical changes, then heterogeneous and homogeneous mixtures that we call solutions, and then compounds, and then, wait for the animation, here it comes, elements. Well, guys, it turns out that that's where we're going to spend not just the rest of this unit, but the next unit and the next unit. So the next 2.5 units, we're going to be talking about elements. Today, we're going to talk about some general things. The next unit, we're going to talk about the nucleus. The unit after that, we're going to talk about the electrons. It's basically going to take us through Thanksgiving. So today, again, those 3 questions about elements. And so, where do atoms come from? We're going to talk about atomic evolution. And you got to be able to answer these 5 questions. Question number 1. And again, skip just one. Skip 1 line between each question so you have a place to write the answer. So question number 1, where did all the hydrogen in the universe come from? If you didn't know this, our universe is actually mostly hydrogen. Then, guys, question number 2, what are stars? Then question number 3, where are the, well, let me say it differently. What is the heaviest element that stars can produce? Then the interesting follow-up question, where do elements heavier than iron come from? And then question number 5, what is the heaviest naturally occurring element in the universe? And guys, you're going to need your periodic tables to think through this, so grab them and get them out. Hey Ryan, while I'm thinking of it, remind me to change your attendance too before you go. You guys all caught up? Not yet? So guys, as you're catching up, let me just tell you, the way we're going to address these questions is I'm actually going to show you a video. The video is by a guy named Neil deGrasse Tyson. He's like the world's biggest teddy bear. He's this really large, if you've ever seen him, he's this really big African-American guy. He's a PhD astrophysicist at Caltech who has got a side job working for NOVA, trying to educate the American populace about science. He's brilliant. They actually brought him to BYU a couple years ago to do a Tuesday morning devotional. Sadly, they couldn't record it. And Tyson is an atheist, it's interesting to know. And he did apparently a really neat Tuesday devotional at BYU, but they couldn't record it because of his contracts with PBS. But I would have loved to have seen it. You guys all caught up? You ready to go? You're good? Okay, so 5 questions, right? Where did the hydrogen in the universe come from? Question number 2, what are stars? Question number 3, what's the heaviest element they can produce? Question 4, where does all the heavier stuff come from? And then question 5, what's the heaviest element in the universe? You're good? Okay, so guys, let me set the stage for you. This is actually a snippet from a NOVA video that Neil deGrasse Tyson is the voice behind. He narrates it. But guys, you sort of need to understand what this is before you can actually understand the video. So here's the way that this goes. Let me tell you the story up to this image. So guys, 14 billion years ago, there was a thing called the singularity. We gave it a name. And this thing, the singularity, interestingly, we don't know how it got there or why it exploded. But guys, this thing called the singularity blew up. We call it the Big Bang. And when it blew up, it expanded. And as it expanded through time, it cooled down. When things expand, they cool. And as it cooled down, it turns out that that singularity contained the universe. So literally at one point in time, 14 billion years ago, the universe was like the size of the head of a pin. And then it blew up, and as it blew up, it cooled down. And as it cooled down, the first thing that condensed out of that explosion was hydrogen. So we may as well answer it right now. Guys, the first question, where does all the hydrogen in the universe come from? The Big Bang. So after that thing banged, it expanded and it cooled, and as it cooled, it turned into atoms, and the atoms that it turned into were the simplest atoms in our universe, which is element number 1, which is hydrogen. So now we've got a universe full of hydrogen. But guys, hydrogen has mass, and if it has mass, it has gravity, and gravity starts to pull these hydrogen atoms together, and they start to turn into clouds. Like this. So now, guys, in our very early universe, we just have these clouds of hydrogen that are coming together. Do you get the idea? Why are they coming together? Gravity. This is where the video picks up. Be nice if we had sound. I'll start it over, but let me grab the sound.
Until something brand new lights up the universe.
Okay, here we go. Do you guys find Tyson's voice soothing? I don't know why, it's like talking to your uncle. Okay, so guys, here we go. Again, clouds of hydrogen.
As hydrogen piles on, the central region grows more and more dense until something brand new lights up the universe. A star. These first stars are hydrogen giants, 100 times or more larger than our own sun. Such massive stars are short-lived, 2 or 3 million years at the most, and they go out with a bang. An explosion so big.
Now understand, that's not the Big Bang, right? That's just a star exploding. You guys know that all stars eventually explode.
They've been dubbed hypernovae.
Do you like the music?
And it's with these cataclysms that the universe begins to accumulate the building blocks of life. All the atoms in the universe heavier than hydrogen and helium are forged by stars.
Stars are really interesting. They don't just sit there. They know because they last so much longer than we do. We think they're permanent.
Stars are the ultimate alchemists. They turn light elements into heavier ones. They get the energy that they need to glow that way. The star begins its life made out of hydrogen and helium mostly, about 70% hydrogen, 28% helium in the case of the sun.
Is that right?
In a star's core, the temperature and pressure are so high that hydrogen atoms fuse together to make helium. Hydrogen fusion releases prodigious amounts of energy.
You guys catching this? So guys, what takes place inside of stars? Lots of hydrogen. What are those hydrogen atoms doing? Fusing together to make what? Helium. So guys, that's fundamentally what happens inside of a star. Hydrogen atoms stick together and they turn into helium. Let's keep going.
The heat and light of a star.
That's the story for 90% of the life of a star, fusing hydrogen to make helium.
Eventually, though, the star runs out of hydrogen.
Got that? So now the star's out of hydrogen. So what do you think it's going to do? Not yet.
And begins to fuse its stocks of helium, making...
So now the star is sticking helium atoms together. And if you stick helium atoms together, what are you going to get? Even heavier elements. You starting to get it?
yet heavier elements.
And so the way it works, and it always works this way, is that it contracts and it gets hotter. And if it can find something new to burn, whether it's the kitchen sink or coal or whatever, it'll burn it.
Helium is taken 3 at a time to make carbon.
You can add one more helium to that carbon and make element number 8, oxygen.
That's a tremendous step forward. You get carbon and nitrogen and oxygen made in stars.
Now this is great because on the board we already have the principal elements of life.
Organic chemistry is the chemistry of carbon.
Carbon fuses next, and still heavier elements begin to form.
Sulfur, argon, chlorine.
Potassium, calcium, scandium. The pace of this gets faster and faster.
Back in the middle, silicon is starting to burn at 3.5 billion degrees.
Billion.
Stupendous temperature.
It makes titanium, vanadium, chromium,
Manganese, cobalt, nickel, and iron.
Iron is really the end of the road. It's sort of the nuclear turnip out of which you just cannot squeeze anymore.
It's the end of the game. A star that has relied on fusion has come to the point where it has nothing more to spin.
The star is suddenly caught in a disaster. There's radiation going out from the outside, but deep in the inside, there's no more fuel.
Iron can't fuel this stellar furnace, and so, when a star builds up too much iron, it dies.
The core collapses, it bounces,
And it begins to move out, first slowly and then faster and faster.
and that sends a very sharp wave back out through the star.
And now what was falling down is going out, the whole thing's blowing up.
Do any of you know the name for that when a star blows up? It's a supernova.
And you've made a supernova.
The supernova explosion can be as bright as 4 billion stars like
You catch that? A supernova is 4 billion times brighter than a star.
the sun.
A stupendous explosion.
Such outrageous energies overcome the iron barrier, cooking atoms into all the rest of the elements on the periodic table.
So starting down here, you can go copper,
Zinc,
gallium,
germanium,
arsenic,
zirconium, niobium, molybdenum, technetium,
strontium,
rhodium,
lutetium,
antimony,
ytterbium,
tellurium,
thorium,
iodine,
radon,
xenon, cesium,
francium,
barium, lanthanum,
tellurium,
cerium,
indium,
actinium,
xenon,
thorium, protactinium,
cesium.
uranium. Done. That's enough elements.
We are all stardust. The carbon in our bodies, the iron in our blood, the calcium in our bones. Every last atom was formed in a star.
You get the idea? Okay, so let's do this as a timeline. Ready? What do we have back here 14 billion years ago? What do we call it? The singularity. What did it do? It banged. It was big. We call it the Big Bang. And that thing expands and it cools. And as it expands and cools, what gets formed? Hydrogen. What do those hydrogen atoms do? Clump together. Gravity pulls them together. As they clump together, what do they eventually become? Stars. Now, guys, and do you guys understand that? The stars, and we'll answer the questions in a minute. Stars are just big balls of hydrogen turning into helium. So, guys, we've got this hydrogen. Did I say helium a minute ago? It's hydrogen. So, guys, hydrogen forms. It all balls together. When they come together, they form stars. Inside those stars, hydrogen is fusing together and makes helium. What eventually happens then? Star runs out of hydrogen. So what's it start to do? Consume helium. When helium starts to fuse together, it starts making heavier and heavier elements. So, for example, helium, which has 2 protons, that's what the 2 means. If you take 3 helium atoms and stick them together, you get carbon. Now we've got the stuff for life. So guys, these stars are then taking helium and making them into heavier elements. And then they run out of helium, and then they start sticking carbon atoms together. And on and on and on until they hit which element? Iron. Guys, iron, element number 26, is the end of the road for a star. Stars cannot produce elements heavier than element 26. So when a star becomes a big ball of iron, what happens to it? It dies, it goes supernova, and it explodes. And all of the energy that is involved in that supernova explosion then fuses iron together to make the heavier and heavier and heavier elements all the way down to which one? Uranium. And guys, uranium is the end of the road. That is the heaviest element in the universe. So guys, let's go answer these questions. You ready? Question number 1, where did all the hydrogen come from? Big Bang. Question number 2, what are stars? They're big balls of hydrogen that are fusing hydrogen together to make the heavier elements. So guys, what that means is when you look up in the sky and you see all these stars, what you're actually seeing is you're seeing big balls of hydrogen fusing together to make helium and other heavier elements, releasing energy in the form of heat and light. So guys, here's an interesting question, and we'll get to the rest of these in a minute, because I wonder if you know the answer to this. What is the closest star to Earth? The sun. I think a lot of you don't understand that. Guys, our sun is a star. Our sun is a big ball of hydrogen becoming helium. So guys, if there are aliens on faraway planets, and if they look across the galaxy back at us, if they are looking at our sun, they see a twinkling star, just like when we look up in the heavens, we see twinkling stars. Guys, every one of those planets could be a sun for a every one of those stars could be a sun for a different planet. And many of them are. So guys, understand that our sun is just another star. And it's actually a very average star. There's not much to it. So you get the idea on stars? Okay. So guys, what is the heaviest element then that stars can produce? Iron. So what about, where do the elements heavier than iron come from? Supernova. As these stars explode. And then guys, finally, what happens as these supernova explode? They take those iron atoms, turn them into heavier elements. But where does this all end? What is the heaviest element in the universe? Uranium. Guys, uranium is element number 92. It's all the way down here. It's wildly radioactive. It actually looks like this. This is actually a chunk of uranium ore. The yellow stuff in there is actually rusted uranium. This was actually dug up down in Moab. I don't know if you know, there's a huge uranium mine down there, but this is what uranium looks like, yeah.
So is it just like happening to be on Earth because like another star like deposited?
That's a good question. Yeah, so how did this all come together? And actually, if you're really interested, look up that video. Just look up Nova, where do atoms come from? That's the next thing he talks about in the video, is how do these things then clump together in big enough portions that we end up with uranium mines and copper mines and gold mines. But it's more than we can go into right now, but it's fascinating, and it's actually, like I said, the next thing out of Neil's voice in that video. Look it up, it's cool. Yeah.
So when the singularity, like the Big Bang, how did it like create all that hydrogen? Was it just like things like super dense or like
How can I answer that without going to jail? Okay, so here's what we know. So Einstein, right? Einstein said something interesting. So Einstein said E equals mc squared. You've heard it, right? So E is energy. M is mass. And then C, I don't know if you know, is the speed of light, and you square it. Not important right now. But the thing that's interesting about this equation is what it fundamentally tells us is that energy and mass are the same things. There is a relationship between energy and mass. And so, and mass and energy. Energy can turn into matter, and matter can turn into energy. They're interrelated. And so what we do know is that singularity was actually not a ball of stuff, well, a little ball of stuff, it was actually a little ball of energy. And when that ball of energy, which is really hard to even visualize, when that little ball of energy banged, as it expanded, it cooled, and energy turned into matter. And that initial matter was protons, neutrons, and electrons, which then became hydrogen atoms. The questions of where did the singularity come from and why did it explode and things like that, we don't know the answer to that. And there are some even atheist physicists that would say we never will, because we're having to go backward beyond the beginning of time, and we can't do that. So yeah, it's interesting. So, you guys okay on these ideas? Anything else you want to chat about? I think I did a good job of answering that fairly. So are we good? We good? Okay. So guys, we are now done with question number 1, which was where do all the atoms come from? Settled there? Okay, so now guys, question number 2. We now know where atoms came from, but the thing that we're going to gain an appreciation of now is just how stinking small these things are. You guys understand that atoms are small, right? Okay. But the question is, how small are they? And this video, frankly, is a little disturbing. Look out for the gorilla. It's not okay. But, so guys, so the question that we're answering now is how small are atoms? Here we go. Are any of you, wait for it. You guys know about TED? If you don't know about TED, you need to go just jump on TED.com. It's an amazing community of really bright people sharing ideas. It's pretty cool. Okay, so TED, here we go. How small is an atom?
You probably already know that everything is made up of little tiny things called atoms. You might even know that each atom is made.
Okay, so this guy's got a really annoying voice. His name is Dr. Bergman. He's also a PhD physicist that made up this video for a TED Talk. And again, the question is, how small are atoms?
Of even smaller particles called protons, neutrons, and electrons.
Now you guys know that, right? You know that protons and neutrons are in the nucleus of an atom and the electrons are zipping around the outside? Okay.
And you've probably heard that atoms are small. But I'll bet you haven't ever thought about how small atoms really are. Well,
Why? Why? I have no idea.
Answer is that they are well, really, really, really small. So you ask, just how small are atoms? Well, to understand this, let's ask this question. How many atoms are in a grapefruit?
Okay, you got it? This is the question we're going to pursue for a minute. Imagine a grapefruit the size of a softball, okay? How many atoms are inside that grapefruit, which easily fits in the palm of your hand?
Well, let's assume that the grapefruit is made up of only nitrogen atoms.
Get the idea? So he's pretending that a grapefruit is just a big ball of nitrogen. Nitrogen is element number 5. It doesn't really matter. He just had to pick an atom so he could determine its size. So we're pretending that a grapefruit is a big ball of nitrogen.
Which isn't at all true, but there are nitrogen atoms in a grapefruit. Well, to help you visualize this, let's blow up each of the atoms to the size of a blueberry.
Got it? So what he's doing now is he's going inside this grapefruit and he is pumping up each of the nitrogen atoms in a grapefruit until they're the size of a blueberry. You can picture a blueberry, right? Okay.
And then how big would the grapefruit have to be?
You get the question? So if we expand the atoms to the size of a blueberry, how big would the grapefruit have to get in order to continue to contain all of those atoms that are now the size of a blueberry? Thoughts?
It would have to be the same size of, well, actually, the Earth. That's crazy. You mean to say that if I filled the Earth with blueberries, I would have the same number of nitrogen atoms as a grapefruit?
Got it? So guys, it takes the same number of nitrogen atoms to fill a grapefruit as it would blueberries to fill the entire Earth. Gets worse.
That's right. So how big's the atom? Well, that's really, 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 really small. And
Do you find that disturbing? Yeah, me too.
you know what? It gets even more crazy.
Okay, so now what we're going to do is we're going to dig in to the inside of an atom. We now appreciate that atoms are really small. So to scale, if atoms were the size of blueberries, then a grapefruit would be the size of the Earth. But now he's going to talk about what's inside of these really small atoms, and it gets crazier.
Let's now look inside of each atom. That's the blueberry, right? What do you see there?
What's that in the middle of the atom? Nucleus. What's in the nucleus? Protons and neutrons.
The center of the atom is something called the nucleus, which contains protons and neutrons. And on the outside, you'd see electrons. So how big is the nucleus? Well, if atoms are like blueberries in the Earth, how big would the nucleus be?
Do you understand the question? So if we took an atom and expanded it to the size of a blueberry, how big would the nucleus be?
You might remember the old pictures of the atom from your science class where you saw this tiny dot on the page with an arrow pointing to the nucleus. Well, those pictures, well, they're not drawn to scale, so they're kind of wrong. So how big is the nucleus? So if you popped open the blueberry and were searching for the nucleus, you know what? It would be invisible. It's too small to see. Okay, let's blow up the atom, the blueberry, to the size of a house.
Okay, so now our atom, the blueberry, is the size of a house. How big then is the nucleus if the atom is the size of a house?
So imagine a ball that is as tall as a 2-story house. Let's look for the nucleus in the center of the atom. And you know what? It would just barely be visible. So to get our minds wrapped around how big the nucleus is, we need to blow up the blueberry up to the size of a football stadium.
Okay, so think Lavelle Edwards Stadium. Got it? So now our atom is the size of Lavelle Edwards Stadium. And if an atom is the size of Lavelle Edwards Stadium, how big would the nucleus be?
So imagine a ball the size of a football stadium, and right smack dab in the center of the atom, you would find the nucleus. And you could see it. And it would be the size of a small marble.
Got it? So if atoms are the size of football stadiums, then the nuclei are the size of marbles. We're going to talk about that next.
And there's more. If I haven't blown your mind by now, let's consider the atom some more. It contains...
Okay, so now guys, you understand what we're saying, right? If an atom is the size of a football stadium, then the nucleus is the size of a marble sitting on the 50-yard line. So guys, the question then becomes this. What else is inside the atom if the nucleus is the size of a marble and the electrons are out in the cheap seats in the stadium? What's between the electrons and the nucleus? Answer? Nothing.
Protons, neutrons, and electrons. The protons and neutrons live inside of the nucleus and contain almost all of the mass of the atom. Way on the edge are the electrons. So if an atom is like a ball the size of a football stadium with a nucleus in the center and the electrons on the edge, what is in between the nucleus and the electrons?
Do you understand the question? And what do you now know to be true? What's between the nucleus and the electrons? Nothing. Guys, there is as much empty space in an atom as there is empty space in Lavelle Edwards Stadium if there's only a marble on the 50-yard line.
Surprisingly, the answer is empty space.
I like the sounds.
That's right, empty. Between the nucleus and the electrons, there are vast regions of empty space. Now, technically, there are some electromagnetic fields, but in terms of stuff, matter, it is empty. Remember, this vast region of empty space is inside the blueberry, which is inside the Earth, which really are the atoms in the grapefruit.
Okay, now, be careful.
Okay, one more.
I can't explain it. I don't know. It's a little disturbing.
Thing, if I can even get more bizarre.
Okay, so now, guys, what he's going to do with the help of this gorilla is he's now going to tunnel into the nucleus. So we started by talking about how small atoms are, blueberries in the Earth. Then we started talking about how small the nucleus is, marble inside of a football stadium. Now we're going to talk about what's inside the nucleus, and this gets even crazier. But let's talk about this. What do you now know about the size of the nucleus? It's ridiculously small, right? But all the mass of the atom is in the nucleus. So it's got a lot of mass and not much size. So what does it have to be? Very dense. Check it out. Excuse me.
Since virtually all of the mass of an atom is in the nucleus, now there is some amount of mass in the electrons.
You're going to miss the gorilla. He's gone now.
But most of it is in the nucleus. How dense is the nucleus? Well, the answer is crazy. The density of a typical nucleus is 4 times 10 to the 17th kilogram per meter cubed.
Got it? That's it. You don't need to write it down. That's the density of the nucleus. And that all makes sense to you, right? Of course not.
But that's hard to visualize. Okay, I'll put it in English units. 2.5 times 10 to the 16th pounds per cubic feet.
So guys, this is a cubic foot. So if this cubic foot had the density of the nuclei of atoms, it would weigh 2.5 times 10 to the 16th pounds. Got it? Still don't got it. Watch this.
Okay, that's still kind of hard to figure. Okay, here's what I want you to do. Make a box that is 1 foot by 1 foot by 1 foot.
Done.
And let's go and grab all of the nuclei from a typical car.
Got it? What's a car weigh? About 2,000 pounds?
Now, cars on average weigh 2 tons. How many
So
cars'
4,000
nuclei would you have to put into the box to have your 1 foot box have the same density of a nucleus?
Got it? So if we wanted the matter in that box to have the same density as an atomic nucleus, what would we have to put in the box?
Is it 1 car? 2? How about 100? Nope, nope, and nope. The answer is much bigger. It is 6.2 billion. That is almost equal to the number of people in the Earth.
So guys, this is what he's saying. If you wanted the matter inside this box to have the same density as the nuclei of atoms, you would have to shove 6.2 billion cars inside this box. And if you shove 6.2 billion cars inside that box, the matter inside this box would now have the density of an atomic nucleus. Of the nucleus. Understand, the nucleus doesn't weigh 6.2 billion cars, but they would have the same densities. So 6.2 billion cars in this box would have the same density as an atomic nucleus.
So if everyone on the Earth owned their own car, and they don't, and we put all of those cars into your box, that would be about the density of a nucleus. So I'm saying that if you took every car in the world and put it in your 1 foot box, it would have the density of 1 nucleus.
Crazy. All right, let's review.
Okay, let's review. The atom is really, really, really small.
Yeah? How small? What do you think of? Blueberries in the earth.
Think atoms in a grapefruit, like blueberries in the earth. The nucleus is crazy small.
So how small is the nucleus? Lavelle Edwards Stadium is the atom, the nucleus is marble.
Now look inside the blueberry and blow it up to the size of a football stadium, and now the nucleus is a marble in the middle. The atom is made up of vast regions of empty space. That's weird. The nucleus has a crazy high density. Think of putting all those cars in your 1 foot box. I think I'm tired.
Wouldn't that have been a good time to bring the gorilla back? They missed it. I know, they blew it. All right, guys, how we doing? 2 for 2? Question number 1, where do atoms come from? Feeling good? Question number 2, how big are these things? And you now understand 3 things. They're ridiculously small, like atoms in a grapefruit or blueberries in the earth. You understand that they're largely empty space, and you understand that they have these even more ridiculously small nuclei, like the marble in the stadium, and those nuclei are not just ridiculously small, they're amazingly dense, like 6.2 billion cars in my box. You got the idea? Okay. So now, guys, we've got one more thing to do. It's going to take us about, 8 or 9 minutes, and then you're going to have time to get your homework done. So here's what you need to do. We are now going to ask and answer the question, what are atoms made of? And you already know protons, neutrons, and electrons. The question is how many? And that's what we're going to do for the rest of the day using our periodic table, is figure out how many protons, neutrons, and electrons are in these atoms. So guys, draw this chart in your notes. Make this chart as wide as your paper and make each horizontal line, each horizontal space 2 lines tall. We'll fill this out. We'll talk about a couple interesting ideas. We'll look at a couple examples, one example. And we'll call it a day. Hey. Nah, we're just gonna make a mess. That's what we did. Yeah, I mean, we just figured it was qualitative, so why mess with it? We just break a bunch of cover slides, so we just let it go. Just wiped up good. I mean, we have some if you want them. Do you want them? Yeah, no, yeah, it's good for them. Are you all caught up? Austin, you look confused. Oh. That means there's somebody looking back at you that's not you? You just looked so intrigued, I had to ask. All right. You're not seeing gorillas, are you? Because you may be after this day. All right, guys, y'all caught up? So I think you know this, right? What are the particles that make up atoms? Well, they're protons, neutrons, and electrons. And guys, if nothing else, you picked it up in the video. Guys, where are the protons and the neutrons? They're in the nucleus. So guys, look right here. The protons and neutrons are in the nucleus, so we give them a generic name. We call them nucleons. So because the protons and neutrons are in the nucleus, we call them nucleons. Okay, so now that you've got that, we're going to fill out this table, first for protons, then neutrons, then electrons, just moving left to right. And frankly, guys, a lot of this is review from what you learned in the previous video, but in a little different form. So, abbreviation, and so this is ABR's abbreviation. So, abbreviation for proton. Make sure you do this just right. So, guys, we abbreviate proton capital P, not lowercase, capital P, and then a superscripted plus sign. So there's information that's contained in that. Guys, I already know you know this one. What's the plus sign mean? Positive charge, right? We'll get there in a minute. But what does it mean that we abbreviate it with a capital letter? And the answer, guys, is it tells us that these are massive. Remember we said that all the mass of an atom is in the nucleus, the protons and neutrons? So guys, protons are amazingly massive. It's actually this. The mass of a proton is 1.67 times 10 to the negative 24th grams. So now you're going, wait a minute. I thought you said they were amazingly massive, but that's an amazingly small number. It's negative 24th grams. And guys, you don't need to write this down, but if you can't visualize this number, it's actually this. That is the mass of a proton in grams. You don't need to know it. You just need to appreciate how ridiculously small it is. So do you see the tension? Protons are really massive, and yet they don't have a lot of mass. So where's the catch? And the answer, guys, is how small they are. For something as small as a proton, this is an amazing amount of mass. They're very dense, like we're talking 6.2 billion cars in a box. So guys, understand they don't have a ton of mass, but they aren't very big, and as a result, they're crazy dense. So, with that said, guys, this is not a number you need to know, and you don't need to know it this way either, because there's actually another unit for mass that we are going to use when we weigh protons, neutrons, and electrons. This is what is called an AMU, atomic mass unit. You may want to write that down if you can't remember. Guys, atomic mass units are AMUs. So here's what they did. They said, okay, we need a new unit of mass that allows us to weigh little things like protons, neutrons, and electrons. So they chose SMART. Guys, they decided that one atomic mass unit is going to be equal to this many grams. Get it? So if an atomic mass unit is equal to this many grams, what is the mass of a proton in AMUs? 1. See how that goes? It's pretty nice. Now, what about charge? You guys all know that protons are positive, but guys, it's not enough to just say positive, it's positive 1. And that's going to be important in just a minute. All right, y'all caught up with me? All right, now go down to neutrons. Guys, check out the abbreviation for neutron. What do you now know about neutrons based solely upon its abbreviation? What does it tell you that it's capitalized? They're heavy. What does the 0 tell you? They ain't got any charge. So guys, how heavy is a neutron? Do you know? It's the same as a proton. Protons and neutrons have the same mass. So guys, if that's true, what is the mass of a neutron in AMUs? 1. It's the same. But guys, what is the charge of a neutron? It's 0. Okay, you good on that one? So what about electrons? Well, guys, check this out. An electron is abbreviated like this. What do you now know about an electron? They're negative, and what does it mean that it's a lowercase e, do you suppose? They ain't got a lot of mass. Guys, all the mass of an atom's in the nucleus. Electrons do have mass, but not very much. They actually weigh this. 9.11 times 10 to the negative 28 grams. Guys, that's about 2,000 times lighter than a proton or neutron. So guys, it takes 2,000 electrons to weigh the same as a proton. So what we do is this. We just round down and call it 0. understand that that's not technically true. Electrons do have mass, but it's so small compared to protons and neutrons, we just call it 0. And then, guys, finally, what is the charge of an electron? And it's not just negative, it's -1. Why is that important? Well, that's important because when a proton and an electron come together, their charges cancel each other. Get the idea? Okay, so one more thing to write down here as we pull this together. So first of all, this, and this is interesting. So guys, what do we now know about protons? Well, they have mass and charge. What do we know about neutrons? They have mass but no charge, and electrons have charge but no mass. So let's group those together. Guys, which two particles have mass? Protons and neutrons. We call those the mass carriers. Now, guys, which two have charge? Protons and electrons. Those are the charge carriers. Now, guys, while we're talking about charge, there's one other interesting thing you need to know about atoms. Atoms don't have a charge. Guys, how can that be? How can it be that an atom doesn't have a charge if they're made of things that have charges? Exactly. So what does that tell you about the makeup of an atom if they cancel each other out? Well, guys, the take-home message in an atom, you will have the same number of protons as electrons. Electrons and protons cancel each other out, so you'll have the same number of both. Is that cool? Okay. So now, guys, the question is, and we're just about done, how do you know how many protons, neutrons, and electrons are in an atom? All that information is on your periodic table, so grab them. So, guys, it goes like this. You need 2 pieces of data in order to figure out what atoms are made of. Look down here at the key on your periodic table. And guys, the information that you need is the big blue number and the little red number. That's all you need, and you can figure out what atoms are made of. So guys, what is the big blue number called? Atomic number. Guys, write this down in your notes. This is called atomic number. It is abbreviated Z. So what good is the atomic number? Well, guys, the atomic number tells us the number of protons in an atom. So you ready for this? Hydrogen is element number 1. What do you know about hydrogen? 1 proton. Where do we find hydrogen? Well, lots of places, but in stars. And what's going on in stars? Well, hydrogen is fusing together, and when 2 hydrogen atoms fuse together, their protons stick together. Now we've got 2 protons, which makes it what element? Helium, element number 2. Then when 2 heliums stick together, we get element number 4, beryllium. When 3 heliums stick together, we get element number 6, carbon, and so on. So guys, those blue numbers tell you the number of protons in an atom, which gets really interesting down here, because guys, look at element 80, which is mercury. What does that tell you about mercury if it's element 80? It's got what? 80 protons in the nucleus. But guys, if we could reach into the nucleus of a mercury atom and pull out a proton, what does it turn into? Gold. And we can do that. If you reach into a mercury atom and snitch out 1 proton, mercury turns into gold. Crazy, right? But guys, that's what determines what an element is the number of protons. So we understand protons. But guys, if we understand protons, what do we also know the number of in an atom? Protons and electrons, they're the same. So now all we need to know is neutrons. And this has to do with the atomic mass or the atomic weight. That's the red number. Now guys, the red number tells us the number of protons and neutrons in the nucleus. It's coming. Now, guys, you're about to have a little crisis. You ready? What are the units on our periodic table for the atomic mass? And it doesn't tell you, so let me tell you what they are. They're AMUs. So those little red numbers are in AMUs. And those little red numbers tell you the number of protons and neutrons. So guys, what is the mass of a proton in AMUs? 1. What's the mass of a neutron in AMUs? 1. Do you see the problem with all the masses on the periodic table? Why are those numbers surprising, given what they are? Tell me more. Who is that? Say more, Gwen. Why are you surprised that those are decimal numbers? Why is that weird? Do you see it? Guys, let's do this. What's the mass of a proton in AMUs? 1. Oh, this isn't turned on. So guys, the mass of a proton in AMUs is 1. What's the mass of a neutron in AMUs? 1. What do you get when you add up a bunch of ones? Whole numbers. So guys, the atomic masses are in AMUs, and the atomic masses are the number of protons and neutrons, and protons weigh 1 and neutrons weigh 1, but when you add them all up, you get decimal numbers. What on stinking earth is going on? It could be the electrons, but it's not. Guys, it's actually deeper than that, and we're going to talk about it on Tuesday. So what are we going to do for now? We're going to round those numbers to the nearest whole number. So when we look up atomic masses, we're just going to round to whole numbers. Okay, so now guys, we're ready to dig into this a little bit more deeply and figure out how to pull all this together. So it goes like this, and we're gonna do a little switch here. So guys, when we represent this, and you want to scratch this down, for elements, we need to represent the atomic number and the atomic mass. And we're going to do it in one of two ways. We could do it like this. 12 over 6, big C. So guys, the big C is the abbreviation for carbon. What is the number 12? Go look up carbon on your periodic table. What's the number 12? Is it the atomic mass or the atomic number? The atomic mass. That's abbreviated A. So we always put A on top. Then 6 is the atomic number. That's the Z. And then the C is the abbreviation for carbon. Now guys, there's another way we can do this. We can do it like this. We can write carbon-12. So we've got two ways that we can communicate this information about atoms. All right, so guys, here we go. We are now going to talk about how many protons, neutrons, electrons are in an atom. We're going to do one example, and you're going to get your homework done. Ready to go? You should be able to answer these questions. If you want to write down the answers, you can, but I don't think you're going to need to. So here we go. Guys, question number 1. How many protons are in an atom? What's the answer? The atomic number. It's Z, right? How many protons are in an atom? The answer is Z. Hydrogen is 1, helium is 2, beryllium is 3. It just keeps going. I'm sorry, lithium is 3, beryllium is 4. So you want to know how many protons are in an atom? The answer is Z. Now, how many electrons are in an atom? Also Z. That makes the charges balance. So now, guys, what's the tricky bit? This one's a little tricky. How many neutrons are in an atom? Can you figure it out? How can you come up with the number of neutrons in an atom? It's a very simple little equation. It's not the same as protons. Look back in your notes. What do you know about the number of neutrons in an atom? How do you find that? What does A tell you? The atomic mass tells you protons and neutrons. So if you just want to know neutrons, what do you got to do? Subtract away the protons, which is what? Z. So guys, if you want to know the number of neutrons in an atom, it's simply A minus Z. The atomic mass minus the atomic number gives you the number of neutrons. All right, you guys good? We're going to apply this once, then we're going to look at your homework, and then you're going to get your homework done. So guys, do this with me. This is worth doing. So here's what I need you to do. Draw a couple circles. Make the little circle an inch across. Make the big circle about 2.5 inches across. And then, guys, go find potassium. Potassium is in the very far left side of the periodic table. It's element number 19, and it has a mass that rounds down to 39. See what I'm looking at? Okay, here we go. So guys, what does the circle in the middle represent? The nucleus. What does the outer circle represent? The electrons. So guys, let's talk about the nucleus. What do you know about the number of protons in potassium if it's element number 19? There's 19 of them. If you want to be a potassium atom, you've got to have 19 protons. If you ain't got 19 protons, you ain't potassium. You got 18, you're not potassium, you're actually argon. If you've got 20, you're calcium. You've got to have 19 to be potassium. Now guys, once we know how many protons there are, what else do we automatically know? 19 electrons. We'll get there in a minute. Let's do the tougher one first. How many neutrons are in potassium? Well guys, how many total things are in the nucleus? Protons and neutrons. How many total? 39. That's the mass, right? So if there are 39 total things in the nucleus, and if 19 of them are protons, how many neutrons have got to be there? 20. Subtract. Then we know that there are 19 electrons because protons and electrons balance. You okay? Now guys, I got to ask you a question. Is this drawn to scale? What if we drew it to scale? Well guys, if we drew this to scale, this circle would have to be the size of a marble. And if this circle was the size of a marble, how big would the big circle have to be? Lavelle Edwards Stadium. You getting a sense of this craziness? So guys, here's the trick. When we draw pictures like this, they can be deceiving because you look at this and your mind just automatically thinks they're drawn to scale. But of course, drawing them to scale is ridiculous. So what are we going to do instead of that? Well, we're going to get away from drawings completely and we're going to do this in tables. Grab your homework. Guys, this is actually your homework assignment. This is exactly it. So let's do the first couple together and let you in on the secrets. It would probably be worth your doing these first couple with me. So guys, the first one that you see is helium. Notice it's abbreviated HE, big H, little e. The atomic number is 2. The atomic mass is 4. So guys, how many protons are in helium? How do you know? So guys, what do you know about the atomic number and the number of protons? They are always the same. Now guys, how many neutrons are in a helium atom? 2. Because it's always the same as protons? No. How do you know? What is it? A minus Z. A is 4, Z is 2. This is 2. Now how many electrons are in a helium atom? 2. Why 2? Because it's the same as the number of protons. You get the idea? Now guys, you'll notice that as you go down through the rest of this, I didn't give you all the information in some instances. But you're like, hey, you didn't even tell me what element it is in number 2. Didn't need to, because what did I tell you? It's element 12, and element 12 is magnesium, so you go magnesium, big M, little g, and you go from there. You guys okay? Okay, guys, you've got 20 minutes to finish these up. You will get done.